it's a great honor for me to be able to speak here. And so I'm very grateful to the organizers. And I remember when I first met Jean-Pierre, it's almost exactly 30 years ago. This was 1994. There's a Résumé summer school on transcendental methods in geometry. And Jean-Pierre gave a series of lectures and about L2 method. And so it was my first trip to Europe. And I was just a very fresh PhD. So I was so impressed about the atmosphere. And I talked to Jean-Pierre. And what was most impressive to me is that he asked me what kind of problem I was interested in. So I told him various problems I was thinking of. And for each of them, he suggested immediately some approach, which sounds plausible. So I was extremely impressed. And then, I mean, after that, we met, of course, very often in the conference and discussions. And what I remember most is he tried to, maybe many of you also feel the same. He tried to educate when he, especially to young people. I'm younger than him, so whenever he talked to me, he tried to educate me. So I miss that part. I mean, not just mathematics, but many issues, especially about what I remember is about nuclear power plant. He's very serious. I mean, it's about this. So I really miss him in this about many things. Okay. So that's a memory. So let me start mathematics. So today I'll discuss some problem, which is an old topic, but many people have forgotten about this. So let me start with the definition. And this is a joint work with Jun-Muk Hwang. Who's in my institute. Okay, in this talk, I'll use the following notation. X is always a complex manifold. And C is a compact complex submanifold. And I'll use this notation, C over X infinity. This is a formal neighborhood of C in X. Okay. And then let's recall the following definition. We say that this submanifold satisfies a formal principle so this I'll abbreviate by FP, formal principle, if the following is true. So that if for any other compact submanifold in some complex manifold with a formal isomorphism, isomorphism of a formal neighborhood, there exists a biholomorphic map of the following type. It's a biholomorphic map from an open set in X to an open set in X tilde, which is a neighborhood of C. And this biholomorphic map induces biholomorphic map on C. So these are biholomorphic. Then we call this satisfied formal principle. So picture, it means that see. So whenever you have a formal isomorphism is slightly thick, infinitesimally thick to infinite order, isomorphism of this infinitesimal neighborhood, arbitrary order. And then it says that whenever you are given such a formal isomorphism, you can always choose some open set. And biholomorphic map like this. That's the formal isomorphism. On the other hand, there's a slightly stronger notion. So it's C in X satisfies formal principle with convergence. So this I will use the notation FPC. If we can choose phi such that we can always choose, we can choose phi such that this formal isomorphism, original formal isomorphism is restriction of the biholomorphic map to the formal neighborhood. Then we say that it's formal principle with convergence. Sometimes people call this strong formal principle. There are many different names, but to avoid the confusion, let me use this, what I mean exactly. Formal principle with convergence. So roughly speaking, formal principle means that formal neighborhood determines a germ of Euclidean neighborhood. If the formal neighborhoods are the same, then some Euclidean neighborhoods are the same biholomorphically. That's formal principle. Formal principle with the convergence, this says that any formal equivalence of formal neighborhoods converges. Whenever you have such formal isomorphism, it must converge. So you can find some neighborhood where it is in fact holomorphic. That's the concept. And from this, it's obvious that formal principle with convergence, of course, implies formal principle. It's a stronger notion, and it's strictly stronger. With a trivially easy example. So consider this example, just one point in the complex line with the coordinates z, coordinates z tilde. And then any formal power series with A1 different from 0 defines formal isomorphism. That's the formal isomorphism. But of course, it does not converge. There are many formal series which doesn't converge. But of course, any 2 points on complex line are biholomorphic. So formal principle is always satisfied. So this say you can see that just one point on any complex manifold actually satisfies Fermat principle, not Fermat principle with convergence. Okay. So from these examples, you can guess the following. That for Fermat principle, usually it's not easy to prove that some submanifold satisfies Fermat principle. It's not usually difficult. But it's even more difficult to find non-example. Examples which do not satisfy Fermat's principle is extremely difficult to find. There's, as far as I know, there's essentially only one example known due to Arnold originally. And there are many other examples, but it's kind of variation of Arnold construction. On the other hand, for Fermat principle with convergence, you can easily get many known examples. But if you just think about it, it's not easy to give examples. Just one point doesn't work. So how, if you ask me for simple example, I don't have a simple answer. So it's not easy to give examples. And fortunately, people study this. And there's this classical result, Commichau-Grauert. And almost at the same time, Hirschowitz. This is in 1981. And they proved that if the normal bundle of the submanifold is sufficiently positive, then this C in X satisfies convergence, Fermat principle convergence. So what's needed is the very positive normal bundle. Now what I'm interested in today is our interest. The weak versions, weakly positive. Normal bundle. Especially I'm interested in, I was always interested in what's called minimal rational curves. Infinite manifold. So I will give you some examples. Because their normal bundle is usually not positive. It's only semi-positive. So it's not covered by this. Okay. One direction. Thomas, let's discuss it. It's written in German. I don't quite completely understand all the. Okay. So let me introduce some weak notion of weak positivity of normal bundle. So some terminology. Okay, let's define this. NC is generically generated if for general point, the global sections of the normal bundle spans the fiber. That's the definition of generically generated. It's a weak notion of positivity. For line bundle, it just means that there's a non-zero section. And another thing is NC is generically, maybe NC generically separate points if for any two general points, the sections of normal bundle vanishing at x is different from sections vanishing at x prime. So it separates points. Okay. So these both are some kind of weak positivity of normal bundle. Now then I have the following result years ago. If normal bundle is generically generated and generically separate point, then a general deformation of C satisfies for my principle. That was what I proved some years ago. So you need only weak positivity of normal bundle, generically generated and generically separate points. These two conditions. Under this assumption, I do not claim that C itself satisfies formal principle, but I claim that if you deform it slightly, then it satisfies formal principle. So this gives many examples, new examples of submanifold satisfying formal principle. So the example I was mostly interested in was when C is rational curve, and this is free rational curve, meaning that the normal bundle is semi-positive. Then general deformation of C satisfies formal principle. Because for rational curve, as long as the normal bundle is semi-positive, it's automatically satisfied. I mean, it's clear. Then it satisfies these two conditions. No, X is just complex manifold, very small, can be very small. Because all the definitions just make sense in the neighborhood of the submanifold. Okay. The question we want to discuss today is about this situation, but when do we have the convergence? That's the question. On the weak positivity of normal bundle, can we still have, in some case, have the convergence? That's the question. This is the question today. Now it's non-example of FP using this theorem? No. So far, there's no good question. As I say, there's no non-example of FP, except Arnold example. So especially, there's no non-example of rational curve, or any simply connected submanifold. There's no example of non-example of FP. If you discover one, I'll be very surprised. I mean, I'll be very happy to hear about it. Okay.
If actions C are added right, does it follow from something like Artin approximation?
No. Artin approximation is about 1 point, not about positive dimensional. So this, we want to know when it converges, but usually there are lots of examples in this situation where it does not converge. And the standard example is, let's look at this bad example. If there's a submersion, so a vibration of this complex manifold to some positive dimensional. Suppose there's a non-trivial submersion such that all deformations of C lie in the fibers. It can happen. The submanifold is in the fiber, and all its deformation still lie inside the fiber. If this happens, then it's obvious that no deformation of C satisfy it's exactly the same kind of argument as this. Just you look at the 1 point there and produce formal isomorphism of 1 point of the base manifold, which is it does not converge. So, and still there are many situations that satisfy this, which admit something like this. You just pick any example and then take product. Then this happens. So you cannot hope that under this generality, you cannot hope the convergence. You need some additional condition. And for this purpose, I will introduce the following. I will say that it's a kind of local version of, to avoid this locally. So this has a bracket generating deformations. That's the terminology. The submanifold has bracket generating deformations if the following happens. If there's no open subset with submersion. Such that all deformation, for any deformation, CT of C, CT intersection O is in fiber. It's a kind of a local version of this. So what I'm saying is that when you have a yes, as a submanifold of X. Yes. You have this, and you have all deformation. But what I like to avoid is that there's some, potentially there's some open set here, and there's a vibration, such that all its deformations are contained, as all deformations intersect this open set inside the fibers. So it's a kind of a local version of this situation. What I really want is a metamorphic version of this situation. I like to avoid metamorphic version of this situation. But since our manifold is not even, is not algebraic, and we don't know what will happen, so in the deformation theory, the deformation may have trouble somewhere. So it's safer to have this definition. It works very generally. So its essential point is to avoid this example. So that's the, so this kind of condition is necessary to have convergence from the bad example. Let's see. Now I need one more technical assumption. This is definition. C in X is unbendable if for general X and any deformation CT containing that point is different from C. The tangent space is different. So what I'm trying to say is that you have this submanifold X. You cannot deform it with keeping the tangent space. This is bendable. Such a submanifold is bendable. You can, because you keep your tangent space and deform. So unbendable means that it doesn't happen. Not possible. That's unbendable. This was if you know the theory of minimal rational curve, this is one of the property to use Morris bend and break method. So it's somewhat technical, somewhat restrictive, but you can see that there are many submanifolds, especially lines, planes. If X happen to be inside projective space, and the submanifolds are like linear objects, and this condition is automatic. You cannot deform it with the tangent space fixed. So here's our first result. Assume satisfies 1, the same as before, same as years ago. So NC is generically generated and separate point. Two deformations. C in X, yes, C is unbendable. And 3 deformations of C is bracket generating. Then a general deformation of C satisfies the convergence. So this is the answer to the question. You can make from here to here, you can add the convergence, but you need two more conditions. One is this unbendability. The other is the bracket generating property. This bracket generating property we know is necessary. Unfortunately, I'm not sure whether this is necessary. But for the examples I'm interested in, especially minimal rational curves, they always satisfy this condition. eventually it will be related to that. Yes, I will discuss it later. That's why we use that name. It's somewhat unattractive name. But okay, then corollary. So X Fano Picard number 1. And K, this is a family of minimal rational curves. It means that it's rational curves of minimal degree which covers the manifold. And assume for general X, Kx, which is members of through X. So this is a kind of subscheme in K. This is irreducible. So let's assume this, that all minimal rational curves belonging to this family through a general point is irreducible family. So let's assume this. Then general members C of K satisfies for my principle of the convergence. In this situation, all three assumptions are satisfied. So you can check this. So example, let me just give one example. So X surface, hypersurface of degree and most n minus 1. Then general line on X satisfies for my principle is a convergence. Okay. So now I can give you explicit example of submanifold which does satisfy for my principle with convergence. Just a general line on such hypersurface. But note that if degree is n, then general line does not satisfy for my principle with convergence. Because when degree is n, general line has exactly a neighborhood like this, the vibration where all deformations are contained in. So it does not satisfy for my principle with convergence. So immersed, I don't want to discuss it, but on hypersurface they are embedded. But here, of course, you are right. I'm slightly cheating. In general, you have to worry about immersion. I don't want to worry about this. Okay, maybe family of smooth minimal rational curve. Thank you. So these are examples. Okay. Any questions so far? Now let's move on. What's the idea? How do you prove something like this? Convergence of formal power series. How do you prove this? So let's look at the idea. So let's consider more general problem. Consider just 1 point. And we have a formal isomorphism. Of course, we have a formal isomorphism. So they are always formally isomorphic. Formal power series map. when does it converge? This is the question. Because eventually our question, to prove the convergence of formal isomorphism of the neighborhood, we have to prove it at every point of the submanifold. We have to prove when you have such a submanifold, eventually formal isomorphism between formal neighborhood gives formal isomorphism between points, formal neighborhood of points at every point. So you have to deal with this question. How do you prove convergence of at one point? Okay, so there's a sort of trivial test of convergence. So if there are holomorphic coordinates, say z1, zn at x, and another coordinate at x tilde. Okay, imagine there are holomorphic coordinates on each side, such that if you push it forward, the coordinate vector field, so for all I, if you push forward the coordinate vector field, then it becomes the coordinate vector field. If this holds, then phi converges. It's trivial. Why? Because this implies that it means that the pullback of this coordinate is just this coordinate. So in other words, the formal power series expression of the isomorphism already converges. That's what it means. So it's trivially it converges. Okay. So that's why I say it's trivial test. It's hardly useful. But there's a slightly different version which is useful, non-trivial test. If there's a holomorphic, what's called absolute parallelism. This is just a name for frame of vector bundle, but when it's frame of tangent bundle, we call it absolute. In differential geometry, it's called absolute parallelism, frames of tangent bundles. So suppose there are holomorphic absolute parallelisms, say V1, Vn at x. And such that the pushing forward by this formal isomorphism of this vector, it's a vector field, of course. This frame is just this frame. Then phi converges. One special example we saw here, if the absolute parallelism come from these coordinates, then here we saw it, that pushing the frame to this frame implies it converges. But actually, this frame need not come from coordinates. just any absolute parallelism, locally holomorphic. As long as it is preserved by the formal isomorphism, then the isomorphism must converge. This you can find in Kobayashi Nomi's book, volume 1. Not exactly in this form, it's essentially there. It's a key to locate where it is. In a sense, essentially, there's only one possible under this condition, and it has to converge. This condition essentially determines all coefficients of the formal isomorphism because it spans every direction. Actually, it's more generally need not be framed by any affine connection, any holomorphic affine connection. The frame is a special case of affine connection. Okay. Why is this useful? So here's our second. Do I have enough time? Okay. Our second theorem is in the situation of theorem 1. Let's consider this universal family of all deformations. I usually use this notion. Universal family of deformations. Of this submanifold. Then this is a statement. Then there is a Zariski open set. Say U inside the universe. And a canonical fiber bundle. With a canonical absolute parallelism. On P. So here n is the dimension of P. So there's some, whenever you have such a family, there's an natural absolute parallelism somewhere. It's some fiber bundle over this universal bundle. But everything is completely canonical. After you go to some fiber bundle, there's a canonical absolute parallelism. Because if you just look at the curve itself, it's difficult to imagine that there's a natural frame. But if you go to some natural space, there is a natural frame. That's the statement of this. And this theorem, of course, this implies the theorem 1. So this theorem 2 implies theorem 1. Why is it this? So choose C general. And pick C general. And assume you have formal isomorphism. We want to show that this converges. let's look at this. So here you have x. C. And you have formal isomorphism. That's the situation. Now you have this universal family in X and also X tilde. So you have a universal family. And then the deformation of this C tilde. So you have a universal family. And then by a theorem 2, you have some natural fiber space over Zariski open set. Maybe it's better to draw a picture. So you have some universal family. This is universal family. And you have the corresponding curve here. And then you have this fiber space. But fiber space is defined only on some Zariski open set. It doesn't matter. OK, so here you have some fiber space. Now, if you have a formal isomorphism between C and C tilde, by the functorial property of deformation theory, it induces a formal isomorphism between the corresponding fiber in the universal family. So it induces some formal isomorphism here. And then because in here I am saying that all the constructions are canonical, such a formal isomorphism actually lifts to some at any point here. If you choose a general point here, then at the point over the general point, you have formal isomorphism of the neighborhood. So the formal isomorphism here induces a formal isomorphism along actually every point corresponding to general point here. But let's pick one point. And we want to show it converges. But we say that over here you have absolute parallelism. This Vi and Vi tilde. And because of canonical nature, it must preserve this absolute parallelism. So it implies that this converges. So phi sharp converges at Y. And then by proper method and so on, you can see that converges at the corresponding point. So this shows that phi converges at general point. At every general point of the manifold, it converges. But from here, you can deduce that it actually converges everywhere at all x. This is the step we need some complex analysis from general to convergence at every point. But this is essentially the only step we need the analysis. The rest is completely geometric. OK, this is why theorem 2 implies theorem 1. OK. But now let's discuss the proof of theorem 2. In some sense, I think the theorem 2 is in some sense more interesting than convergence. Because it says that under reasonable geometric assumption, you have a natural frame somewhere. So what is how do you prove something like theorem 2? No, they are holomorphic frames in a neighborhood of Euclidean neighborhood of the point. Yes, this is what I mean holomorphic frame. Yes. Thank you. Maybe I'll not. Okay. So what's the idea behind this? The idea of this construction is from differential geometry. And this, let me introduce the terminology. Complex manifold. M. A pair of integrable subbundle E of the tangent bundle is, so the pair E is called a pseudo product structure. It's an unattractive name, but that's what they use. So I abbreviate as pseudo product structure. What is a pseudo product structure? It's just two foliations which intersect transversely. So any two integrable submanifold whose intersection is 0. That's called pseudo product structure. You see, if they span the whole tangent space, then this is a product. The manifold is product of. So then it's product structure. Pseudo product structure means that it looks like product but doesn't span the whole tangent bundle. Okay, let me erase here. And then when you are given a pseudo product structure, you define this distribution. So although E and F are integrable, there are some need not be integrable. And that's where the interesting thing happens. Then now D is bracket generating. That's what we want to define. If you have the successive Lie brackets, of local sections D spans the tangent bundle at general end. That's the definition of bracket generating distribution. And then D is Levy non-degenerate. If you have this Levy form, just defined by Lie brackets of local sections of D. There's a natural tensor at every point. And if this is non-degenerate, is non-degenerate. The meaning that is essentially meaning that for all vector, non-zero vector in EX, there is a F such that EF X is not in D, and vice versa. So that's the non-degenerate side. So these are definition of a distribution, bracket generating, and Levy non-degenerate. And another notion is that so when you are given M and EF pseudo product structure for general X, there's a graded Lie algebra. Called the symbol of this pseudo project structure at X. This is essentially determined by these brackets, and these successive brackets. It determines certain graded Lie algebra. I will not discuss the precise definition, but you can imagine that there's some natural Lie algebra at general point. And we say that EF has constant symbol if these are all isomorphic. All general point. So these are Lie algebra at every point, at every general point of X. If the isomorphism type of this Lie algebra doesn't change, then we say that it is a constant symbol. So these are the conditions. What time is it? How many minutes? 5 minutes. Symbol is, I didn't define it exactly. Is some graded Lie algebra which is determined by these brackets. Some a finite dimensional graded Lie algebra. For contact, suppose these contact structure, then it's Heisenberg algebra. Okay, maybe after. And here's the big result that we need to use. This is called Tanaka prolongation theory. So it says that EF is pseudo product structure on M, and D is bracket generating and Levy non-degenerate. And assume constant symbol. So he needed this three conditions: bracket generating, Levy non-degenerate, and constant symbol. Then there's a Zariski open set. And the canonical fiber space. With a canonical absolute parallelism. On P. This is called the Tanaka prolongation theory. So whenever you have this structure, satisfying rather natural non-degenerate condition, but he needs a constant symbol, then he can construct this. There's some natural inductive construction which gives this. That's what he proved. And this is, by the way, general. How he come up with this kind of, the paper is like more than 8 pages long and extremely complicated induction. The reason is it's a generalization of his work in 8 years ago. There's 1962. He first defined this Tanaka connection for Levy non-degenerate CR structure. And it's an ultimate generalization of that work. Okay, so that's how you come up with this abstract notion. Now our theorem 3. In theorem 2, in this situation, let E be kernel of D mu and F kernel of D rho in this direction and this direction. Then EF on M is now universal family, is satisfies. It's a pseudo product structure. Satisfies bracket generating and Levin ungenous. And actually, from the first theorem 1, the bracket generating condition exactly corresponds to bracket generating condition here. And the other two conditions give Levin undegeneracy. Okay. So you are almost ready to apply Tanaka prolongation theorem to this proof here, because that's exactly the statement we need. But we need one condition, this constant symbol. And that, unfortunately, is not true. Especially like if you look at hypersurface, lines in hypersurface, it cannot be true. The symbol cannot be constant. The isomorphism type of this Lie algebra changes. So we cannot apply Tanaka prolongation directly. So here's my last theorem. Oh, it's overtime, I'm sorry. Let me just state the last theorem. The last theorem is generalized Tanaka prolongation. And it just says that we don't need constant symbol in symbol assumption in Tanaka. That's how we obtained it. I'm sorry.